Hi everyone. Today I'm going to talk about parallel Python. And as you all know, there are some exciting development in Python for parallel computing. We have sub-interpreters and free threading. And the main goal of this talk is to share what it is out there and how things are shaping up. And before I begin, I would like to thank all the volunteers who have done awesome work to make this event great. About me, great. Yes. And about me, I'm ML engineer at IdenTV, and I also pursuing my master's in Georgia Tech, and I'm also volunteering since last 3 years for EuroPython and other conferences like Python Ireland. So before I begin, there are a few disclaimers, and I have also added a few links over the footnotes so that anyone could go more in detail later. So first thing is, don't go over for the benchmarks, because benchmarks depends on the use cases you have, library used, environment it is tested on, and the code, how it is written, and how it is interacting with the network or the hardware. And also, there are a lot of new things going on, like sub-interpreters and NoGIL version of Python. It is accepted in the PEP, and there are releases, but if it is accepted in a condition that it might be reverted back if it is found to be too disruptive. So you might have to wait for all of your packages updated in order to make it change on the production. So I have a question first. How many of you have heard about free trading or sub-interpreter before? Okay. And how many of you have first-hand experience with it? Okay. So thanks to all the core developers we have in CPython and the person involved in this project, we have a very exciting paradigm shift in parallel computing. And there are a lot of discussions about how we should implement this project. And I think all of us can use this project in their own hobby project and then give feedback to the community. And because the steering committee also looking for the feedbacks over the forums, how it should be there. So let's begin. Why care about parallelism? If you ask a random Python developer about the same question, he will probably say, or like the developer might say that he already know about multi-threading. This is one of the example. You can create threads in low-level way like this. In Python, everything is a process. We have an interpreter, and then you can spawn as many threads as you like. This is just a low level, as I said, but if you need high level with better error handling and the thread pool support, you can use the concurrent, which is quite good. But these solutions are only for concurrency. You don't achieve the real true parallelism with multi-threading. So if you want the true parallel processing, you might use multiprocessing, which is super cool, industry tested, but then it has some overhead on the memory. But it can use all of your cores if you are going for that. And there are also other options like coroutines, async IO, and there's also a talk about async IO later today, so you can also see that. So these are the options we already have. So let's test it out first. This is just a small function where we are doing NumPy processing, and this is just a sign and cost thing. But let's test it out on a simple machine. We are doing multi-threading, multiprocessing, and the sequential run. Here, I have also used the shared memory. What do I mean by shared memory is it is created based on the requirement we have here, the floating point, and it is created on a memory space and will be attached to every process that multiprocessing will be spawning on. So, but there is some issue with shared memory. The thing is, when a process exited like quite quickly, and there are some shared memory attached to it, then the resource tracker will delete that shared memory, which is not cool if the other process that is alive is also rely on that shared memory. So if we are going to use shared memory, we have to also be cautious about how we are exiting the process. So back to the question, which one do you think will be faster? For the, any guesses? Okay, that's a good guess. So here, here's the result. We can see that multiprocessing didn't perform good because it's way worse than sequential. But then threading, we have some improvement. And but the multi-threading didn't scale well if we add much number of threads. And also, the shared memory also improved the performance for the multiprocessing. So it's a good thing. But this is not what you do in production. You are not going to do the sine and cos. What I want to do is replace this function with the usual thing in machine learning, that is calculating the magnitude of a vector using norm function in NumPy. And the same process, just changing the single computation, we can see different result, which seems weird. Because as you zoom in this graph, the multiprocessing bar goes off the chart, and then with the multithreading, it didn't do any optimization whatsoever. And even the shared memory didn't save the multiprocessing. So let's look underlying thing, like what is happening right now. Since we are not using the standard library, we are using NumPy, and NumPy has its own optimization. In the left, we are seeing element-wise, and the right, there is vector optimization based on the NumPy. And if you dig more deeper in NumPy documentation, you can see that NumPy is releasing the GIL, and thus it is improving the threading in Python. So that's how they are doing it. And if we see the header file from the NumPy, this is how they are using macros called npy release allow and the end thread to release the thread. So here what it is doing is it saves the thread state of Python in some local variable, and then release the GIL, and then do some computation, and then reacquire the GIL, and then restore the thread state, and then do all this Python process that we have. And this is quite common. In CPython, we can find similar code in Socket and the other libraries like Arrow. And you could find many other libraries are releasing the GIL. So my main question is GIL is the problem? And that's why people are releasing the GIL to get the performance needed from Python. So let's dig deeper in GIL. So when I talk about GIL, I want to recommend a video from David Grizzly. It's quite old, but this is one of the first whistleblower showcasing the impact of GIL in a very detailed way. It was showcasing the new GIL, which was introduced in 3.2, but it shows like how the GIL is impacting the multi-threading performance in Python. So let's visualize it. Let's say I'm spawning 3 threads, and GIL is responsible to run 1 thread at a time. And due to the GIL, it also manages the context switching. So here in the first, in the starting part of the diagram, we can see that thread 1 is context switched to thread 3. So we can assume that there is no real parallelism when we are using the multi-threading. This is quite common, but what if we want to see this in the real code? You can actually do that, and I did it using Python 3.8, using vtracer and the perf package. And you can create multiple thread, and then you can literally see in your own CPU that when thread are running, when the GIL is releasing, and how it is working under the hood. But the vtracer didn't work on the latest Python, because with latest Python, we have some issues I'm gonna explain on detail more. So let's see more on GIL, because it is one of the reasons that David mentioned we have problem with the multi-threading. So GIL was there before I was born. So GIL was there. It was so old, and everybody was writing C extension, assuming it was there. It also protect the global state. It prevent us from race conditions, deadlockings. But I want to put in a different way. Since GIL was there, people were also starting and adopting Python in other domains like healthcare or any other stuff right now. So they feel like, okay, GIL there. Let's don't figure out about race conditions, because it will protect us from all this state. So which makes us this scenario where if we want to remove the GIL, we will have a lot of problems. And there are attempts to remove the GIL, but they are all slow compared to the sequential one. And so if we or if some developer wants to remove the GIL, they have to deal with a lot of issues with C extension and the ABI changes. And even if someone could able to remove the GIL, they have to use locks and the immutable objects, which are the new thing that are added in Python. I also want to highlight few of the parallelism projects that are being done, but it didn't really useful in the community. People have tried changing interpreter. There are Gilectomy from Larry Hastings. There are Parallel, which was there for Windows only. And then there are some other tools like Dax and Taichi, which are different tools, but it's really hard to integrate that thing in our standard library. And there is multiprocessing, but As you can see in the documentation of multiprocessing, in Windows, you can't really scale up to more than 61 processes. So, and it also needs a lot of optimization to really use it in the production. And if you say you don't need the code, then you can just use the async IO, which is quite helpful for many other use cases. So now this led me thinking like, what's new now? We have two things: free threading, which is NoGIL version of Python, and the sub-interpreter. The free threading project is led by Sam Gross, and from outside, we can just see that it is just removal of the GIL, but under the hood, there are a lot of optimization. And in the sub-interpreter project, led by Eric Snow, we have multiple interpreter in a single Python process, which seems a lot better than the multiprocessing. And it is interesting how we can use it right now in our project. So for free threading, we can install a new build of the same version of Python using pynb and other stuff. And then for sub-interpreter, for Python 3.13, we have to install a new package. So let's deal more about sub-interpreter right now. So in the left, we can see that before Python 3.11, we have one process and one interpreter pair. We have GIL there controlling all the states and all the modules. And then we can spawn any number of threads there and do multi-threading there. But in the new version of sub-interpreters, we can create multiple different interpreters that runs parallelly under the same process. Here, each interpreter has its own module. What I mean by module is all the classes, functions, variables, whatever you have loaded, even the C extension, all will be copied independently in the interpreter so that each independent interpreter can run in isolation and won't interfere with each other. This was a hard thing to do because there are some global state. So what happened right now in Python is like a lot of global state are trimmed down to interpreter level so that there won't be needing interpreter communication between this. So just a thought, why do we need sub-interpreter right now? So one argument I came up for is CPython already have support for sub-interpreter since 1997. And so why not use it? Because it has some benefit over multiprocessing, as there are less number of global state compared to multiprocessing. And also, it looks quite similar to multiprocessing as well. So what's the difference? So the difference is quite obvious. The first thing is we have a single process in sub-interpreter, but then different in multiprocess. What I mean by different process is like when spawning the multiprocessing, it will copy everything from all your modules in a separate process. But here, we don't have to do all this copying in memory. So it is also quite fast to create, and it has less overhead. There's also a claim that the communication in sub-interpreter is quite good, but it's experimental, and there's a nice video about that as well. But it's in the experimental phase, and we might not see the result. But in multiprocessing, it is quite robust. It can support pipe, queue manager, and can do everything, every kind of data structure. Even though it uses the pickling, it supports everything. But in sub-interpreters, we are now starting to implement every data structures to communicate between them. So let's dig more deeper how much good benefit we can get with the interpreter. So first thing is startup time. We can assume there is around 5x improvement based on the discussion from the forums. There are many different community members who are benchmarking between sub-interpreters and the multiprocessing. And there's one catch here. Some older Python version of before 11, I guess, might use fork method to create the process. So the forking is like just copying everything we have in a process, just putting it into different process. But then there's a different method called spawning, which is creating everything in memory from the scratch, which might take more time. So where does the sub-interpreter lies? Sub-interpreter lies between the forking and the spawning. So that's how we got some improvement over startup time. So you can spin up more interpreter fast than the process in multiprocessor. And also, we can share a lot of objects in sub-interpreter. Here's the list. And can you guess what's the similarity between all these data structures? So just to give you the answer, these are immutables. But memory view is a mutable data structure, and how it is going to transfer between the interpreters is it just copy from the reference the values of memory view and then transfer it to the interpreter. And in order to use the mutable type, we have to use the lock to ensure the thread safety in our program. So these are all the features of sub-interpreters. How can we use it, and what's the structure right now? So if you check for the interpreter blog and all this benchmarking, you'll see this kind of code where the interpreters is hidden beside some of in the standard library, and we are running a small string in the interpreter method, but it will only run in 3.12. Why? Because the PEP that include multiple interpreter in the standard library is deferred. Why? Because we are still discussing about the correct way method for creating the sub-interpreter. And as you know, the Gen of Python, there should be one obvious way to create and running the thing here. So we are still figuring out like whether to add run, exec, or call. Right now, the function of run is removed in Python 3.13, but we are using exec and call. And for Python 3.13, we have to install a separate library as it is deferred. Right now, what's the project leader, Eric Stone, mentioned that let's try it as a Python package, and people will test it out, will use it in the different project, and a new PEP will be there for the sub-interpreter. And hopefully in 3.14, we can add it in our beloved concurrent module. So this is about sub-interpreter. Let's talk about field threading. So before talking about field threading, which is just basically removing the GIL, we have to talk about reference counting. And what is reference counting? So here in Python, every object has three types. One is the type of an object, and then value, and the reference count. If we decrease the reference count to 0, garbage collector kicks in and removes the memory block. And this process is non-atomic. Why? Because it will make sure that Python runs faster, being non-atomic. And being non-atomic is the problem, because if we want to run multiple threads without the GIL and this non-atomic function, then multiple threads want to reduce the reference count to 0, which will eventually delete a lot of memory from the object, and eventually it will crash the program. So we have bias reference count, which is sum of local thread as well as the shared reference count. And it is based on the idea that when you create a thread and the thread has a lot of variables, most of the time you use those variables within that thread. You generally don't do the communication between the threads about the variable. And that makes us to create a non-atomic for the local reference count, and then atomic if you are sharing the variable between the thread. This also reduces a lot of reference counting contention issues and useful for free threading. There are also other improvements done over the free threading, which is memory allocation. They rewrote everything out from the scratch. And then there's also a concern about thread safety, because once you remove the GIL, you are on your own, and you have to make sure that you create locks, and you should create the locks in such a way that there won't be any deadlocks. And there are also like special will for CPython, and we need to make sure that every libraries that we are using under our code should also support this. And there's also a new ABI changes, which make it hard for the backward compatibility issue. I purposefully didn't add any code slide in this free threading because nothing is changed. All your multi-threading code will work same for free threading as well, just we have to change the Python version. And it's just like Python script.py, it will run. So let's see the benchmarks number. Here I'm calculating the Fibonacci number, and the complexity rise from in the x-axis from left is quite easier to do calculation. On the right, we are calculating much higher number of Fibonacci. And this graph is based on log. So you can see that in this scale, multi-threading is performing quite worse. And then the other stuff like sub-interpreter, multiprocessing, and free threading are performing quite same. There is no difference whatsoever I could find in the diagram if we are comparing the highly computational load. But then if we are checking the low computation, then multi-threading is working good. This can be there can be one reason for that, because Python works on the tick level, and then calculating the Fibonacci on for lower number is quite easy to do. Then multi-threading do it way faster than all the other stuff. If we see the same benchmark in a linear scale, we can see that multi-threading is quite bad on the high computation. And then if you zoom out this end part of highly computational part, we can see that multiprocessing performing a little bit worse. We have sub-interpreter in between and the feed threading at quite efficient, but there is no such significant impact. And this is the very beginning phase of this project, and we can see some optimization going on later as well. But it shows a quite promising result with using threading. So what to use, free threading or sub-interpreter? That's the major question, right? So first of all, can you write the thread safe code, or can you verify that your code is thread safe? Then you can use free threading. Otherwise, don't go with that route. Wait for some time. And then if you're not, then you can use sub-interpreter, because even though you have different interpreter, we have GIL attached to each interpreter, so all your C extension will work. You don't have to care about GIL. But even though you don't want to use the sub-interpreter because it's a different package, maybe it's not robust, then you can just use the Python 3.13 as well, because there are a lot of improvement over that as well. So if you go for anything between free threading and sub-interpreter, you have to check whether your library support it or not. And for every library right now, we can see multiple different issues, pull requests going up, and if you want to contribute as well, you can contribute right now. It's a golden opportunity because everything is rushing to support this free threading and sub-interpreters. So what to do now? It's quite confusing because maybe your library does not support it. So there's a blog post about it, and in this blog post, it is more explaining about how you can convert your library to support free threading. And there's also issue tracker where you could see top 300 most popular Python package, whether it's support or not. So once you figure out your library is supported, you will also need to check it. So PyTest right now don't support the free threading, but there are other alternatives like PyThread, runPaler, and PyTest free-threaded, which will help you to test out your program will run on free threading or not. But here's a catch. Let's say you didn't find any mention from the library that whether it supports the free threading or not, and you pip installed it and it worked. Then still you might need to check from sys module. Why? Because it can re-enable the GIL if the library does not support it. And why is it so? Just to make sure that even though you install a library that does not support the GIL, and you are running the GIL-less version of Python so that the whole Python process does not crash, it re-enables the GIL by default. So you have to still check after using the library whether the library support. Now, with all this information about free threading and sub-interpreter, I hope we all explore this realm of parallel computing in Python. And having said that, that's the end of my talk. Thank you.
So, any questions?
Any questions? Yeah.
Okay, then if not, if you have any questions later, please feel free to have a chat with the speaker after today. And then I guess we can move on to the next speaker.
Thank you.